June 22, 1940, Calais, France. Hauptmann Werner Schulze stood in the rubble of a bombed-out warehouse, staring at the twisted remains of a British tank. The armor had buckled under German anti-tank fire, peeling back like torn paper. He knelt beside the hull, running his gloved hand across the steel. Something was wrong. The metal felt different, rougher, inconsistent. He called over his metallurgist, Lieutenant Hans Becker, who'd spent peacetime analyzing industrial steel in the Ruhr Valley. Becker examined the armor under magnification, then looked up with confusion. "This isn't military-grade steel," he said quietly. "This is structural steel, railway steel, maybe 50, 60 years old." Schulze stared at the wreckage with new understanding. Britain hadn't just lost an army at Dunkirk, they'd lost everything. And what they were rebuilding it with wasn't coming from factories, it was coming from their past. Before we continue with this remarkable story of desperate innovation, take a moment to like this video and subscribe to the channel. We bring you these forgotten chapters of World War II history every day. Drop a comment below telling us where you're watching from. Now let's return to June 1940, and the crisis that would force Britain to dismantle itself to survive. The British Expeditionary Force had evacuated from Dunkirk 3 weeks earlier. Operation Dynamo had saved 338,000 men, but left behind nearly every piece of heavy equipment the army possessed. The numbers told a catastrophic story. Britain retained fewer than 100 operational tanks on home soil. Artillery pieces numbered in the hundreds when thousands were needed. The army that returned from France was intact as men, but stripped of everything required to fight modern war. Churchill's demand was clear and impossible in equal measure. Rebuild the army's equipment within 6 months. Not just replace what was lost, but exceed it. Create an armored force capable of defending Britain against the Wehrmacht that had crushed France in 6 weeks. The industrial reality made this fantasy. Britain's tank factories could produce perhaps 20 vehicles monthly. At that rate, equipping even one armored division would take years, and Germany was preparing for invasion. Herbert Morrison, Minister of Supply, stood in his Whitehall office studying production schedules that offered no hope. Every calculation ended the same way. Conventional factory production couldn't possibly meet the deadline. The meeting with Churchill had been brief and brutal. "Find a way," the Prime Minister had said. "Britain has 6 months before invasion becomes possible again in spring. Use whatever methods necessary. Conventional production won't suffice." Morrison understood what Churchill wouldn't say aloud. Think beyond factories. Think beyond everything tried before. The solution arrived from an unexpected source. A junior civil servant named Thomas Wright, working in a cramped procurement office, had been reviewing trade statistics from the previous year. Britain had imported American scrap metal before the war. Old railway cars, bridge sections, derelict machinery, substantial quantities of steel that already existed, already smelted, already distributed throughout the country. Wright's memo reached Morrison's desk through bureaucratic channels. "We cannot build new steel fast enough," Wright wrote, "but we possess enormous quantities of existing steel in forms no longer serving their original purposes. Could it be repurposed?" Morrison convened an emergency meeting with metallurgists, engineers, and military procurement officers. The question was dangerously simple. Could you melt down a Victorian railway bridge and turn it into a tank? The metallurgists were skeptical. Steel came in different grades, formulations, tempers. Railway steel wasn't armor steel. You couldn't just melt random objects and expect consistent military-grade results. But Arthur Davies, a shipyard engineer with 30 years of practical experience, disagreed. "Consistency isn't the issue," he said, leaning forward. "We're not building precision instruments. We need armor plate, gun shields, tank hulls, relatively simple shapes from relatively crude steel. Railway steel is high carbon, quite strong. Bridge sections are structural grade suitable for supports and frameworks. It won't be optimal, but it will work. And gentlemen, we have it now. Distributed across every town in Britain, ready to be collected and reshaped." Morrison made his decision that afternoon. Britain would strip itself of obsolete steel infrastructure and convert it into military equipment through a decentralized network of workshops, foundries, and improvised facilities. No single factory would produce the Army's equipment. Instead, thousands of small operations would each contribute pieces, assembled into finished weapons through coordination rather than centralized production. The program was named the National Steel Reclamation Initiative. Within days, government notices appeared in every newspaper, posted in every town hall, announced on BBC broadcasts. Britain needed steel, and Britain would provide it. Citizens were asked to identify obsolete steel objects in their communities. Old railway equipment no longer in service. Derelict bridges scheduled for replacement. Unused industrial machinery. Retired trams and buses. Even decorative ironwork from the Victorian era. Gates, fences, railings deemed non-essential. The response overwhelmed expectations. Local committees formed within hours. Volunteers with cutting torches and heavy equipment descended on identified sites, systematically dismantling steel structures that had stood for generations. In Birmingham, a Victorian railway viaduct became the first major target. Built in 1847, it had been replaced by a modern route, but still dominated the valley with 7 massive arches. The structure represented 19th-century confidence, over-engineered by contemporary standards, constructed with far more steel than modern calculations required. Dismantling it required 3 weeks of continuous work. Engineers surveyed weak points and safe-cutting sequences. Workers with acetylene torches cut through girders 3 feet thick. Sections that had supported trains for 93 years now destined to become tank armor. The work was dangerous. Workers operated at height with cutting equipment, dealing with steel that had been stressed by decades of use. The metal was unpredictable, sometimes cutting cleanly, other times fracturing as internal stresses released. 3 workers were injured during the operation. One fell when a section shifted unexpectedly, breaking his leg and ending his contribution to the war effort. But the work continued without pause. The viaduct yielded 400 tons of structural steel, all high-quality material suitable for military use. Local residents watched the dismantling with conflicted emotions. The viaduct had been a local landmark, visible from miles around, part of the landscape for 3 generations. Now it was being erased from the skyline, cut apart and trucked away to be melted down and reformed into weapons. Progress measured in destruction. Mary Thompson coordinated collection efforts in Sheffield, managing operations at 30 sites across her district. Her diary from those months provides intimate detail of the program's scale and complexity. August 12, 1940. Survey team identified derelict railway bridge near Rotherham. Estimate 80 tons recoverable steel. August 15th. Received complaint from town council about removal of Market Square railings. Explained necessity. Council reluctantly agreed. August 22nd. 40 tons of machinery parts collected from closed foundry. Owner initially refused access, changed mind after visit from government official. The entries captured both the logistics and the emotional cost. It felt like we were dismantling Britain to save Britain, she wrote one evening. Every piece of removed railing, every section of retired bridge represented Victorian prosperity and engineering achievement. We were literally cutting up our past to forge our future. The steel moved through an improvised logistics network. Railway wagons carried bridge sections to foundries. Trucks transported machinery parts to workshops. The system was chaotic but effective, driven by urgency that eliminated usual bureaucratic delays. Within 6 weeks, 50,000 tons of reclaimed steel had been collected. Within 3 months, 200,000 tons. The quantities were staggering, representing decades of accumulated industrial infrastructure now being repurposed for immediate military necessity. Back in Calais, Hauptmann Schulze continued his investigation of captured British equipment. More tanks had been examined, and the pattern held. The armor wasn't consistent military-grade steel. It showed variations in composition, thickness, even color. Some sections were clearly newer than others. Some bore markings that suggested industrial rather than military origin. Schulze compiled a detailed report for Wehrmacht intelligence. British armor production appears to be utilizing non-standard materials, he wrote. Possible explanation: severe shortage of military-grade steel forcing use of civilian industrial materials. Quality is inconsistent, but generally adequate for defensive purposes. Recommendation: British industrial capacity may be more severely damaged than intelligence estimates suggest. The report reached Berlin in early September. Analysts studied it carefully but drew the wrong conclusion. They assumed British industry was so damaged it could only produce inferior equipment. They failed to grasp the actual innovation. Britain hadn't been forced to use inferior materials. Britain had deliberately chosen to utilize existing resources rather than wait for conventional production. The Rose Foundry in Yorkshire exemplified the transformation occurring across Britain. Before the war, owner George Rose had produced cast-iron drainage pipes and industrial fittings. In July 1940, he received 40 tons of reclaimed railway steel and instructions to produce armor plate sections for tank hulls. Rose was skeptical. "We've never worked military steel," he told the government engineer. "Don't have specifications or testing equipment. Don't even know what thickness armor needs to be." The engineer was blunt. "Thickness is 3 inches. Steel is what you've received. Testing will happen during assembly. Your job is to cast sections to provided templates, deliver them to collection point, and start the next batch. We need 200 sections monthly. Can you do it?" Rose studied the templates. Simple rectangular sections with bolt holes pre-marked. Not precision work. "We can do this," he said. "When do you need first batch?" "Yesterday, actually. Deliver them next week and we'll call it acceptable." The foundry converted its entire operation within days. Workers who'd cast drainage pipes now cast armor sections. The techniques were similar, but the product entirely different. Furnaces needed higher temperatures to properly melt the harder railway steel. Molds had to be reinforced to handle different expansion characteristics. Cooling times were longer because sections were much thicker than anything previously produced. Rose brought in metallurgists from the local university to advise on conversion. Together they calculated proper furnace temperatures, cooling sequences, finishing procedures. The first batch emerged after 2 weeks of experimental runs. Half were rejected. Too brittle, improperly cooled, dimensions off specification. But the other half passed inspection. "We learned by doing," Rose later recalled. "No time for extensive testing or gradual refinement. We'd cast a batch, send them for inspection, adjust based on feedback, cast another batch. Within a month, our rejection rate dropped from 50% to 20%. Within 3 months, down to 10%. We became quite good at making tank armor, which was remarkable since we'd never imagined doing such work." The foundry operated continuously during peak production. 3 shifts, 8 hours each, keeping furnaces hot and molds in constant use. Workers who'd spent entire careers making drainage pipes now took pride in producing armor that would protect British soldiers. The change in product and purpose transformed workplace morale despite brutal conditions. Quality was variable. Some sections were too brittle, others too soft. But volume compensated for inconsistency. If 3 sections failed testing, the 4th usually passed. The approach was wasteful by peacetime standards but effective under emergency conditions. Across Britain, similar transformations occurred in hundreds of facilities. Workshops that had never produced military equipment became part of a distributed supply chain, each contributing specialized components that would be assembled elsewhere. The challenge became coordination. How do you assemble tanks from components produced in 300 different workshops? Lieutenant James Crawford supervised an assembly operation in a converted warehouse near Birmingham. Each week, trucks arrived with components from across Britain, armor sections from foundries in Yorkshire, turret assemblies from workshops in Wales, track links from facilities in Scotland, engines from wherever automotive works had spare capacity. It was like the world's most complicated puzzle, Crawford later recalled. Nothing fit perfectly. Every tank required modifications during assembly. We'd receive armor sections 2 inches too wide, so we'd cut them down. Track links that didn't quite match, so we'd file them to fit. Turret rings that bound instead of rotating smoothly, requiring hours of adjustment. Crawford's team consisted of 30 workers. Skilled tradesmen too old for military service, reserved workers with essential skills, and women who'd learned metalwork in weeks-long training courses. They assembled tanks in a warehouse that had previously stored textiles, working under a corrugated metal roof that provided minimal protection from weather. The assembly process was systematized despite necessary improvisation. Each tank began on one end of the warehouse floor, marked out in chalk. Hull components were laid out and welded together first. Base plate, 4 side sections, front and rear armor. This alone took 3 days because every joint had to be welded carefully to ensure integrity. Then the turret assembly was mounted, requiring precision despite crude components. The turret ring had to rotate smoothly or the gun couldn't be aimed effectively. Track assemblies were fitted next, connecting dozens of individual links into continuous bands. The engine and transmission were installed from above, using an overhead crane that had been part of the warehouse's original equipment. Finally, internal equipment. Gun sights, communication equipment, ammunition storage, seating for crew. Much of this came from conventional military supply, but even here, improvisation was necessary. When proper military radios were unavailable, civilian equipment was modified. When specified seating couldn't be obtained, simple steel frames with canvas padding substituted. Each completed tank took approximately 2 weeks to assemble, meaning Crawford's facility could produce roughly 6 tanks monthly. That pace frustrated him because he could see where more workers or better equipment would accelerate production. But the government had to balance resources across hundreds of similar facilities, each demanding more support than could be provided. Quality control was minimal by conventional standards. Tanks were tested by driving them around the assembly facility and firing main guns at a nearby quarry wall. If they moved and shot, they were declared operational and shipped to Army units. The vehicles weren't elegant. Welding seams were crude. Armor sections showed visible gaps. Mechanical components rattled with imprecise tolerances. But they worked. The tanks could move, their guns could fire, their armor could stop expected German rounds. By October 1940, the distributed network was producing 80 tanks monthly. By December, 150 monthly. The numbers weren't matching German production, but they were transforming Britain's defensive capability from nearly nothing to substantial armored force. The human cost of this achievement was carefully documented but rarely discussed. Thomas Wright, the civil servant whose idea had launched the program, maintained casualty statistics never publicly released. Over 6 months of peak production, 47 workers died in industrial accidents directly attributable to the steel reclamation program. Hundreds more suffered serious injuries: burns, crushed limbs, respiratory damage from foundry fumes. The first fatality occurred in July 1940, barely 2 weeks after the program began. A crane operator in Liverpool was positioning a large section of bridge steel when the cable snapped. The 5-ton section fell, striking him instantly. The accident was attributed to equipment failure. The crane had been operating beyond designed capacity. Morrison received the report the same day. He read it carefully, authorized compensation for the worker's family, issued directive that all lifting equipment should be inspected before each use. But he didn't slow collection operations. The urgency remained absolute. More accidents followed with grim regularity. In August, a foundry worker in Sheffield was overcome by fumes from an improperly ventilated casting operation. He collapsed near an open furnace and suffered severe burns before co-workers could pull him clear. He died 3 days later in hospital. In September, a welder at an artillery shield workshop in Manchester was electrocuted by faulty equipment. The welding apparatus had been operating continuously for weeks, maintained minimally, pushed beyond designed capacity. An insulation failure energized the equipment. When the welder touched it while standing on damp concrete floor, he was killed instantly. Each death report reached Morrison's desk with brief description of incident and preliminary assessment of cause. He insisted on reading every report personally, refusing to delegate this responsibility. His staff noticed he aged visibly over those months, the weight of casualties adding to immense pressure of the overall rearmament effort. Morrison visited accident sites when possible, meeting with families, ensuring they received compensation and support. But he never slowed the program. The math was brutal. 47 workers had died producing equipment that might save thousands of soldiers and prevent an invasion that could kill tens of thousands of civilians. By January 1941, 6 months after Dunkirk, the British military conducted assessment of equipment situation. The results surprised even optimistic observers. Britain now possessed 800 operational tanks, compared to fewer than 100 in June. Artillery pieces numbered 3,000, up from several hundred. Armored cars, self-propelled guns, anti-tank weapons had all increased dramatically. More remarkably, 80% of the equipment had been produced through the distributed network using reclaimed steel. Less than 20% came from conventional factory production. The tanks weren't sophisticated. German Panzer IIIs were superior in armor, firepower, and reliability. But Britain now had numerical advantage and defensive positions. German invasion would face armored resistance rather than a nearly defenseless army. General Alan Brooke, inspecting armored units in southern England, was candid in his assessment. These vehicles wouldn't survive long in offensive operations against prepared German positions, he told his staff. But for defensive warfare, particularly in Britain's favorable terrain, they're adequate. The Germans would pay a terrible price trying to advance against this force. In occupied France, Hauptmann Schulze received orders to prepare a comprehensive analysis of British armored capabilities for the Wehrmacht General Staff. He'd examined dozens of captured and destroyed British tanks by now, documenting their construction in meticulous detail. His report was damning in unexpected ways. British armor demonstrates systematic use of non-standard materials, he wrote. Steel composition varies significantly between vehicles and even within individual vehicles. Welding quality is inconsistent. Component tolerances are crude by German manufacturing standards. However, the vehicles function adequately for defensive purposes. More significantly, production appears to be increasing rapidly despite our earlier assessments that British industrial capacity was severely damaged. Conclusion: the British have developed alternative manufacturing methods that do not rely on conventional factory production. This suggests greater resilience than previously estimated. Schulze included photographs of armor sections showing visible variations in steel quality, welding techniques, and construction methods. He noted markings on some components that suggested civilian industrial origin rather than military manufacture. He documented how different vehicles showed different design approaches, as if produced by separate facilities working from common templates rather than standardized factory production. The report reached Wehrmacht intelligence in February 1941. Analysts studied it carefully, recognizing implications they'd missed before. Britain wasn't just recovering from Dunkirk. Britain had fundamentally changed how it produced military equipment. The distributed manufacturing approach made British production resistant to strategic bombing. There was no central factory to destroy, no critical bottleneck to target. Production was dispersed across thousands of small facilities, each contributing to the whole but none essential individually. The realization came too late. Hitler's attention had already turned toward Operation Barbarossa and the Soviet Union. The invasion of Britain was postponed indefinitely, then abandoned entirely. Whether British defensive preparations deterred German plans or whether strategic priorities had simply shifted remained debated. But Britain's rapid rearmament had been a factor in German calculations. The National Steel Reclamation Initiative ended in spring 1941 as conventional production expanded and American Lend-Lease equipment became available. The distributed workshops returned to normal operations. The improvised assembly facilities closed. The extraordinary effort that had transformed Britain into a distributed factory ceased to be necessary. George Rose converted his foundry back to civilian production in 1942, but kept templates from the armor sections his workers had cast. We made 2,400 sections over 18 months, he later reflected. Each one weighed 400 pounds, took 3 hours to cast, and would stop a German shell if welded properly to a tank. I kept the templates to remind us what an ordinary foundry could accomplish when extraordinary circumstances demanded it. The program's achievements were remarkable not just in quantity, but in innovation. Britain had proven that industrial capacity wasn't limited to formal factories. That distributed production networks could achieve results centralized systems couldn't. That urgency could overcome technical limitations through determination and innovative thinking. In 1985, a military museum in Kent acquired a tank from the 1940 production run. The vehicle was in remarkably good condition, despite 45 years in storage. The restoration team examined it closely, documenting its construction with modern analytical tools. The tank was a patchwork. Armor sections came from at least 4 different foundries, identifiable by slightly different casting marks. Track links showed 3 distinct manufacturing styles. The turret assembly used a mix of standard military components and improvised parts machined in unknown workshops. Most striking was the hull's base section. The museum metallurgist identified it as railway steel from the 1880s based on composition and microscopic examination. Somewhere in Britain, a Victorian-era railway component had been dismantled, transported to a foundry, melted down and recast as tank armor, then assembled into a finished vehicle and deployed to defend against invasion. This tank represents triumph of improvisation over industrial limitation, the museum's director wrote in the exhibition catalog. Every component tells a story of distributed manufacturing network that transformed Britain's obsolete infrastructure into military equipment when conventional production proved inadequate. It's not beautiful, but it worked. That was sufficient. Herbert Morrison rarely discussed the steel reclamation program after the war, but in a final interview before his death in 1965, he reflected on those desperate months. "We did what was necessary with what we had," he said quietly. "Britain couldn't outproduce Germany through conventional methods. We lacked the factories, the time, the resources, so we abandoned conventional methods entirely. We turned the entire nation into a distributed production system using accumulated industrial infrastructure from the previous century as raw material." He paused, looking out the window at modern London rebuilt after the Blitz. It worked because British people made it work, not through heroic individual actions but through sustained collective effort. Every worker who cast armor sections in a converted foundry, every volunteer who dismantled obsolete infrastructure, every engineer who assembled mismatched components into functional vehicles. They built the army that defended Britain. Morrison's voice grew softer. "We didn't win through superior technology or industrial capacity. We won through willingness to completely reimagine how military equipment could be produced when traditional methods failed. That's the lesson I hope endures. When conventional approaches prove inadequate, innovation and determination can create entirely new solutions from existing resources." The steel reclamation program was largely forgotten in post-war histories, overshadowed by later industrial achievements and military victories. Few books mentioned it. Official histories focused on conventional production and American assistance, but in workshops across Britain, older workers remembered. The foundry owner who'd cast armor sections, the workshop supervisor who'd machined tank components, the assembly line worker who'd welded mismatched parts into functional vehicles. They remembered transforming obsolete railways into modern weapons, remembered the urgency, the innovation, the sheer determination to create an army from the nation's accumulated industrial past. They remembered proving that Britain's strength lay not in its factories, but in its capacity to transform every workshop, every foundry, every available resource into instruments of survival. Britain built an army of steel in 6 months without a single dedicated factory by becoming the factory itself. Every reclaimed railway section, every dismantled bridge, every obsolete machine was transformed through a distributed network of improvised facilities into the weapons that defended the nation. The tanks weren't beautiful. The artillery wasn't sophisticated. The equipment was crude by technical standards, but it existed when existence itself was the challenge. And in that moment of desperate innovation, when Victorian bridges became modern armor and obsolete railways became instruments of defense, Britain discovered that survival sometimes requires dismantling the past to forge the future. That was enough.